Hi, I'll explain our work, Multidimensional Byte Pair Encoding, where we bring the tokenization algorithm that makes LLMs viable to image generation. Autoregressive transformers don't like long sequences. Rather than using single characters, text is usually put together into larger chunks by byte pair encoding. This trades sequence length for vocabulary size as a lossless compression scheme. Our idea shows how we can bring this idea to visual data like images while taking full advantage of the two-dimensional neighborhood relations of pixels and image regions. On a higher level, byte pair encoding makes use of data being spread in a non-uniform way. Certain character sequences occur very frequently and hold little information. Byte pair encoding puts these text snippets into a single new token. It does so by first counting all pairs of tokens, then replacing the most frequent one with a new character, repeating these steps until the desired vocabulary size is reached. Just like in text, for visual data like images, information is also spread out in a non-regular fashion. Some parts in the blue sky in this image contain little information, while other regions are much more detailed. Similarly, repeating patterns also offer potential for compression. Nonetheless, most of the representations all follow similar ideas to turn images into regular grids of tokens. These are then sequentially generated. While there exist approaches that stray from regular grid representations, the focus of autoregressive generation is usually on linearized sequences of such regular grids. Our goal is to give autoregressive generation the same boost that text-based methods get from combining frequently co-occurring tokens into new ones, trading an increase in vocabulary size for a decrease of sequence length. Since classic byte pair encoding is limited to 1D sequences, 2D grids must be flattened prior to its application. This process results in a loss of spatial context, thereby missing out on some of the inherent properties for compression. We propose to lift byte pair encoding into multidimensional form, hence calling our approach Multidimensional Byte Pair Encoding, or short, MDBPE. We require a quantized representation. For images, we demonstrate this on grayscale images, VQVAE tokens, VQ-GAN tokens, or simply color quantized images. For MDBPE, a token is a connected region of pixels. Our core algorithm uses the same principles as regular byte pair encoding. First, we count the co-occurrences of neighboring pairs of tokens, initially just the superpixels of a VQVAE or grayscale pixels. Initially, these are just the superpixels of a VQVAE or grayscale pixels. We slide over the image, counting all horizontal and vertical configurations for all different images in the dataset. Second, we replace the most frequently occurring token combination with a new token. This is repeated until we reach the desired vocabulary size. The key to turning byte pair encoding into a truly multidimensional approach is the counting procedure. As two adjacent tokens can be in very different constellations to each other, we have to distinguish those cases. We use a simple dictionary for counting. Initialized at 0 occurrences, we use the combination of the two token indices and an offset vector describing their constellations to uniquely identify the constellation of the tokens, then increment this for this occurrence. When going over the grid from top to bottom, left to right, we take a token, then identify all neighbors. We then increment the counter for the dictionary entry corresponding to the found combination of token IDs and offset vector. For each neighbor, we define the offset vector going from the most top, most left point of the token as the anchor point of the neighboring token. The vector from the anchor point of the neighbor to the anchor point of our original token, together with the token IDs of both tokens, then uniquely defines their constellation, and we increase the corresponding entry in the dictionary. After going over all images and all tokens, we find the token combination with the largest number of occurrences. We then replace these two tokens by a new single token everywhere in the image. We then repeat this procedure until we reach the desired vocabulary size. To generate a sequence, we take our now irregular 2D grids and turn them into 1D sequences, from top to bottom, left to right. We then train an autoregressive transformer architecture to reproduce these sequences. During generation, we now go over the grid and fill the first unoccupied grid cell with what the transformer outputs, clamping probabilities of tokens that do not fit. Then we find the next unoccupied grid cell again, fill it, and repeat. While these more compact sequences can already be generated easier by an autoregressive model, we apply two further tricks to make the sequence produced by our approach more digestible, in addition to the usual positional embeddings for our token. First, additionally giving the transformer the information on where the next token is going to be. This is uniquely defined through the previous sequence of tokens. We always add the positional encoding of the next unoccupied grid cell to the previous token. Second, we help our transformer by providing information on which space each token occupies in the grid. We add the additional description of the occupied cells to each token. To describe the cells that a token occupies, we integrate over all positional encodings of all positions that a token occupies in the grid. For discrete grid cells, this is simply a sum over all positional encodings of the token. Experiments on our shortened sequences show a number of advantages. Note that all we do is a pre-processing step. Training happens just as usual. First, our transformers converge more quickly. Even when disregarding all speedups we can gain from having shorter sequences and hence larger batch sizes, our model converges much faster to better results than a vanilla transformer on discrete tokens. Second, for our results, we observe that sequence length negatively correlates with the training speed of a transformer. Hence, we can evaluate results in terms of sequence compression ratio. Note that even reducing the size by just a few % can mean a lot. We mainly attribute this to two separate observations. First, shorter sequences are much easier to learn. The attention mechanism is known to dilute with longer sequences, meaning difficulties to focus on the right pixels for context. Having one larger token to focus on through attention can also be easier for a transformer, as the softmax in the attention layer forces one single peak in the attention, which now can be a whole region instead of just a single pixel. Second, combining something from larger blocks also means less room for error. When stacking sampling process on top of sampling process, the probability of deviating from the distribution seen in training due to the transformer not being perfectly trained grows exponentially. With shorter sequences made from larger blocks that are coherent within themselves, this risk is drastically reduced. This does not negatively impact diversity, as can be seen by comparing generated phases to the most similar ones from the training data. Our approach also has the advantage that it can be applied to different data modalities. We are not restricted to 2D sequences, but can also apply our algorithm in 3D to produce voxels or SDFs. While this video already covered most of our approach, we invite you to read our paper for the exact details and additional extensions like further improving sequence compression through collapsing VQGAN tokens to make image generation even more affordable.